That's about chain isomerism, the first kind of structural isomerism. Let's move on to study the next class of structural isomerism, that is position isomerism. Now, position isomerism will be compounds or isomers in which the functional group would be the same, but the position of that functional group could be different. For example, if we have propanol, normal propanol, 3 carbon in a chain and then OH group in the terminal end. So this is propanol, this is normal propanol. We can have 2 propanol where this alcoholic group, where this hydroxy group is on second carbon. Now, first of all you have to check, do they have same molecular formula? If they don't have same molecular formula, they cannot be isomers. Now, before checking out which kind of isomers they are, first of all, you have to see if they have same molecular formula. If they don't have same molecular formula, they cannot be isomers. So, there is no point looking at the kind of isomerism. Now, once we have checked that they have the same molecular formula, then let's see whether they have same functional group. Yes, they do have same functional group, and the position of that functional group is changing. So that is the positional isomerism. That they exhibit positional isomerism and they are positional isomers. Fine, simple, easy. Now suppose you have to draw the positional isomer of 2 butene. Now apart from functional group, they can be double bond and triple bond as well. If the position of the pi bond is changing, then also they will be said to have positional isomerism. For example, if we have 1 butene. Now, do 1 butene have a scope of showing position isomerism? Now, this position of pi bond can change. It can come to this position. Now, the numbering presently is like this. So, it is 1 butene. Now, this can show isomerism in which the position has been changed to second carbon. So, it can become 2 butene. So, 1 butene and 2 butene have different positions of pi bond and they have same molecular formula. So, they are position isomers. Similarly, you draw the structure of a position isomer of 2-pentanone. And you also draw the position isomers of orthoxylene. First of all, deal with 2-pentanone. Now, pentanone, pent means having 5 carbon and one means ketone and 2 means on second carbon. So, 5 carbon and a ketonic group on second carbon. This is 2-pentanone. I have done the numbering from the right hand side. You can do it from left hand side as well. Just flip this. So this is 2-pentanone. Now, can this have a position isomers? Because the position of the functional group in this case have to change. This is ketonic group. This ketonic group can come on the third carbon as well. So of course it will show position isomerism, and this could be the positional isomer of 2-pentanone. This is 3-pentanone. So the position of functional group has changed, so they are position isomers. Simple. Now xylene could be troublesome if you don't know the formula of xylene. Now, this being troublesome is okay, but having heard of xylene once and not being able to recall it when you heard it next time in your life, then it's troublesome, and then that is problematic. If you don't know xylene, no problem. I'm telling you, this is xylene. Now know this from now. When you have 2 methyl groups sitting on benzene ring, that is called xylene. Now they are at ortho position with respect to each other. If you consider 1 carbon on which the one methyl is attached, the first position just adjacent to it is ortho. The next is called meta, and the next is called para. Now this position is similar to this position, so this is also meta. And this position is similar to this, so this is also ortho. Now the methyl groups are at ortho position with respect to each other, so this is orthoxylene. Had it been at meta position with respect to each other, then that would have been called as metaxylene. And similarly, paraxylene. They are asking you to draw the position isomer of orthoxylene. Now, orthoxylene will have much different chemical and physical properties than metaxylene, which will have different physical and chemical properties with respect to paraxylene. So you have to draw the position isomers. So the functional group will remain same. Actually, there's no functional group as such here, but the compound will remain same. It will be xylene. If you change the position of methyl group, you are supposed to get positional isomer. Although there's no functional group here, although the position of pi bond is not changing, but still the molecular formula is remaining same and the properties are changing, and this fits the best in the category of position isomerism. So if they ask you to draw the isomers of position isomers of orthoxylene, then you just get a isomer where you have this methyl at meta position or para position. So actually it will have two isomer, metaxylene and paraxylene. That's it. Suppose they give you four structures like this, and this, and this, and finally this. Now let's name it A, B, C and D. Question number 1. Which of the above are positional isomers? Now A, B, C, D. Choose two compounds which are positional isomers. A pair of compounds which are positional isomers. Now look at A. Positional isomers, the basic skeleton of the carbon have to remain same, and the positions of either functional group or pi bonds or substituent have to change. Now substituent will also fall into the category or will qualify for positional isomerism. Now the substituent here is chlorine, and the position of chlorine is changing. There's no functional group, there's no pi bond, but the position of substituent is changing, and the basic structure of the carbon is same. The skeleton of the carbon is same. If you look at A and B, skeleton of the carbon is same and the position of chlorine is changing, so they are positional isomers. So A and B are positional isomers. If you look at C and D, if you look at the basic skeleton of the carbon, you have an iso group here. You also have an iso group here. If you look at, they may seem a little different. If I draw D like this, now this is same as this, right? I have just rotated it 90-degree anti-clockwise. Now they look similar. If you see, there's 3 carbon in a chain and 1 methyl is on second carbon. There's a 3 carbon in a chain and 1 methyl on second carbon. Same as this. 3 carbon in a chain and 1 methyl on second carbon. So they have the basic carbon skeleton as same, and the position of chlorine is different. So they are positional isomers. A and B are positional isomers, and C and D are positional isomers as well. So that's it. Positional isomers pair is A and B and C and D. If they ask you which are chain isomers, then here we don't have chain isomers, because if you look at A and B, actually A, B and C and D don't have same molecular formula, because it has 3 carbon and they have 4 carbons. So they will not have actually chain isomerism. So that's it.